Wait. Sorry, you couldn't hear anything. Could you hear me at all? Can you hear my alarm? Man, this is it's okay. Could you hear my prayer? Well, let's do it now. Father, Son, Holy Spirit, amen. This is the beginning of a new day. God has given me this day to use as I will. I can waste or use it for good. What I do today is important because I'm exchanging a day in my life for it. When tomorrow comes, day will be gone forever, leaving in its place something I've traded for it. I want to be gain, not loss, good, not evil, success, not failure. In order there should not regret the price I paid for it. For the future's whole string of nows. Mary, Queen of Victory.
Pray for us.
Pray for us. Okay, so let's get going here. I am going to. What? I don't want this. I'm going to share the whiteboard. Hopefully you can see the whiteboard. If not, you're going to have to let me know. So anyway, so we looked at I wanted to finish up with what we talked about yesterday. Yesterday we looked at this function, the greatest integer function or step function, and we noticed, you know, the domain of f is all real numbers. However, it's continuous not on its domain, so it is not a continuous function. It's continuous on all real numbers excluding the integers, because there is a jump discontinuity at every integer. So we actually have a jump there. So it's not fixable. So it's an essential discontinuity everywhere there's an integer, right? Because of the jump there. So it is not a continuous function. It is not continuous on its domain, but it is continuous. We talked about on including 0 to not including 1 definition, union including 1 to not including 2, etc. Going both ways. We had that. If you actually take the union of all those sets, you end up getting all real numbers. However, because of the definition of what it means to be continuous on an interval, it is not continuous on all real numbers, even though the union of these sets is all real numbers. But it is continuous on all reals excluding the integers. So that was just kind of what we did at the end of the day yesterday, kind of a unique thing there. So now let's go on and do the last couple items in this section. The first theorem is the intermediate zero theorem. So it's called the intermediate, which means in between, zero theorem. Proven fact. I'm going to call this IZT for short. And as we talked about yesterday, there's a couple different words for a zero of a function. So we're not talking about the number 0. We're talking about where the height is 0, which is also an x-intercept where it crosses the x-axis, or another word for that is a root of the function. So that's what we're talking about. So we have an intermediate height of 0, and it's where we cross the x-axis. So what this theorem says is, it says let f be a function, which anytime I write f, it's a function, so I'm not going to write that part, but we're going to let f, our function, be continuous on the closed interval a to b. So we're going to be able to draw our function without lifting our pen through the endpoints. We're going to have right-handed continuity at x equals a, and we're going to have left-handed continuity at x equals b. And we're also going to let f of a and f of b have opposite signs. So f evaluated at a and f evaluated at b are going to have opposite signs. That means one is positive and one is negative. Okay, so one's above the x-axis and one's below the x-axis. Then what we're going to know is there exists some number c strictly in between a and b, so not an endpoint, but strictly in between, such that the height, when you evaluate it at C, is going to have to equal 0. Okay, so I'm going to draw a picture of this, and it should make sense. But this is a couple of things that we're assuming is that f is a function that's continuous on the closed interval, and that the endpoints have opposite signs, meaning one's above and one's below axis. Essentially, what we're guaranteeing is there's some point in between that you have to cross the x-axis. So let me draw a picture of the intermediate zero theorem. Couple of pictures. So here's A, here's B, and if I draw my function, I'll use a different color. I'm going to say in this case, f of A is greater than 0, right? So there's f of A. That's positive, and here's f of B, which is negative. Okay, so they have opposite signs. I drew the graph without lifting my pen. I should do it a little smoother. Let me just kind of go like that. Anyway, just make a nice function there from A to B. Basically, what we are guaranteed here is by the theorem, since I'm continuous here, there's at least one point strictly in between the open interval, not including A to not including B, such that f of C, f evaluated at C, equals 0. In other words, C is a 0 of the function, meaning the height there is 0. C is a root, or C is an x-intercept. The point C, f of C would be the point C0 is an x-intercept there, right, for the x-axis and y-axis. So we have something that could look like that. Let's look at a couple other options here. So I could have from A to B. Similarly, I could start out below and then go to above. There's a continuous function. Well, here's my C in between, right? So f of A is negative, f of B is positive. There's going to be at least one point there. So let's look at yet another option here. If I have something like this, what do we notice? We notice that f of A is positive, or also f of B is negative. We also have a continuous function that I drew there, so we're assuming from x equals A to x equals B that this is a continuous function. But what we notice here, there's actually 3 different places where we cross the x-axis. So it is okay to have more than one. So we have 3 points here, C1, C2, and C3, that are all x-intercepts, where f of C1 equals 0, f of C2 equals 0, and f of C3 equals 0. So we could have more than one. We could actually have infinitely many points as well. And let me just show a real quick picture of that. If we have from A to B, and then I draw my function, if I have, we could go down here, and then I could go straight across, and then I could go down here. This is still a continuous function the way it's written. So if I have 3 different line segments, that line segment is continuous, that line segment is continuous, and this line segment is continuous. So I am continuous on the closed interval A to B. However, now I have infinitely many values of C in there, right? So basically there's infinitely many x-intercepts. But what does the theorem guarantee? The theorem guarantees that no matter what, if we know we are continuous on the closed interval and have right in a continuity at x equals A, whoops, coming in there, and left-handed continuity at x equals B, and if I know that one of my points is above and one of my endpoints, and one of my endpoints is below, that I have to, if I have continuity and draw this graph without lifting my pen, and it's a function, which means there's only one height for one output for every input, that there has to be a c strictly in between. So that's what the theorem says. Pretty obvious, hopefully, on your end that this is the case. So let's look at a specific example using the intermediate zero theorem. Let's look at f of x equals x squared minus 2 on the closed interval, including 0 to including 2. Basically, we need to show the intermediate zero theorem holds, or holds true, or basically applies, and find the c that satisfies the theorem. Okay, so here's what we're going to do. First of all, if I graph this thing, this is a downshift of the x squared, right? So really, it's a downshift of the parabola, and then of course I'm going from 0 to 2. So when I plug in 0, I get -2, right? And when I plug in 2, I get 2 squared minus 2, which is +4. So actually it goes out here. So that's +4. So this is my graph right here. And I think it's pretty obvious that the intermediate zero theorem is going to hold, but I need to find this c, which is strictly in between 0 and 2. So we have to first show that the theorem is satisfied. So f is continuous on the closed interval 0 to 2. Can somebody put in the chat function why that's the case? Well, we're not there yet. Can you just tell me why f is continuous on that closed interval? So here's my function f. Why is that continuous on that closed interval? You're answering a future question. You can draw without lifting your pen. That's correct. What else kind of function is that? So in this case, we know what it looks like, but you may have an awkward function that you can't graph, or you're not sure what it looks like quickly. Can anybody else chime in? What kind of function is f here? It's a polynomial. Perfect. So this is true because f is a polynomial. Polynomials, we know, are continuous. So I'll put a check mark because we have continuity on the closed interval. Polynomials are continuous on all real numbers. Therefore, it's going to be continuous on any subinterval, whether it's open or closed or half open, half closed, doesn't matter, because it's continuous on -infinity to +infinity. So we have that. And then we also have to show the other part is that f evaluated at the endpoints has opposite signs. So f of 0 is negative, which is less than 0, and f of 2 equals positive. Whoa, 4 minus 2. What's 4 minus 2? Isn't it 2? Somebody should have told me that was wrong. 4, I didn't subtract the 2 there. So anyway, if I plug in f of 2, I actually get +2, right? Which is greater than 0, so they have opposite signs. So I have that as well. This one's positive, this one's negative. Therefore, what do I know? Therefore, the intermediate zero theorem says there exists a c strictly in between 0 and 2, such that what? F of c equals 0. Okay, so that's a backwards epsilon, so that's a such that f of c equals 0. So now we need to find that c. Okay, so remember, f of x is x squared minus 2. So f of anything is that anything squared minus 2. What's my anything down here? It's a c. So that just says simply that f of c equals 0. So c squared, instead of f of x equals x squared minus 2, f of c is c squared minus 2. That's going to equal 0. And then we just solve that. So in this case, you could use a quadratic formula here because we have a quadratic. So anytime you have quadratic equation set equal to, or quadratic set equal to 0, you could use a quadratic formula. But in this case, it's easy to solve because I can just add 2 to both sides and then take the square root. And then, of course, when I take the square root, it's plus or minus, correct? So I have 2 options here. C is plus or minus the square root of 2. Square root of 2 is about 1.414. So which one is in there? So in that open interval, so C equals the square root of 2 is an element of the open interval, not including 0 to not including 2. So our answer is the positive square root of 2. The negative square root of 2 doesn't work for our answer. So even though there was 2 options, there was only one that was strictly in between 0 and 2. Just real quickly here, if I would do the other side of that parabola, and I went from -2 to 0, to basically I'd be continuous there, right? But the C here would actually be the negative square root of 2, or about negative 1.414, etc. Right? So that's an element of the open interval. We were working on the right side. So when you solve that equation, make sure that you pick the one that works. So any questions on the intermediate zero theorem? Hopefully the answer is no. Should make a lot of sense. Why do we use the intermediate zero theorem? Because you have an even exercise that's due on Monday from section 1.9, but it leads to, so that's actually a preview theorem, or a theorem that leads to another theorem. So it's a lemma to the next theorem. So this next theorem, which is a corollary to the intermediate zero theorem, is called the intermediate value theorem. So the intermediate value theorem is the next one. So once again, a proven fact. Now, when I say the word value, I mean height value. So just like 0 meant a height of 0, which meant an x-intercept or root, the intermediate value theorem is the intermediate height theorem. Okay, so height of your function. So what does this theorem say? I'm going to call this IVT for intermediate value theorem, is going to be my shorthand there. We're going to have very similar things. Let f be continuous on the closed interval. So f is a function, obviously, and is continuous on the closed interval a to b, meaning we can draw without lifting our pen, not only in between, but kind of through or hitting the endpoints as well. Right-handed continuity at A, left-handed continuity at B, and continuous on the open interval. And then the other thing, instead of having opposite signs, which if the endpoints had opposite signs, they can't be equal. If one's positive and one's negative, they can't be equal. But in this case, all we need is that the endpoints are not the exact same height. Okay, so f of A and f of B are not the same. Then what can we say? Then there exists a C strictly in between A and B, such that what? Well, such that f of C equals K, and let's kind of think about this. So what K is a height, right? It's f evaluated at C. But if I just draw a picture real quick of a function where the endpoints aren't the same, there's f of A, there's f of B. I'm continuous, right? The endpoints are not equal. F of A does not equal f of B. Basically, f of C is a height, K, so there's some height K. So in this case, K is a height. So here's f of x equals K. That's a height. But there has to be, any height in between K has to have at least one C that maps to it. So in this case, f of A is strictly less than the height K, which is strictly less than the height f of B, which is not the case in this case. The other one is f of B is going to be less than K, so it's below K, which is going to be less than f of A. And that's actually the one that I have here. So for the picture I drew, I actually have this. But basically, there's going to exist at least one C in between that maps to any height strictly in between. Okay, if you'd rather write the second part that I circled in red, you as f of A is strictly greater than K, which is strictly greater than f of B, you could do that as well. Instead of switching the f and the A and the f of B, you could just switch the inequalities. So anyway, so I have that. So that's the intermediate value theorem, which if you notice, really, I could take that and drop it down with a symmetry, like I could do a horizontal shift downward. And basically that C that I got there, if I drop down to K less than where that function heights are for every point. So if I look at a base graph, and so the G of X would be your f of X function minus K for every height would be lowered by K. It's a downshift, right? I would, by the intermediate zero theorem, be crossing X equals 0 instead of, or excuse me, f of X equals 0. Your height would be 0 instead of at K. So this is basically a downshift. The intermediate value theorem is nothing more than a up or down shift. In this case, my picture, it was a downshift, but it's an up or down shift of the intermediate zero theorem. And there's going to be at least one point that maps to a specific height of K. All right, so let's look at a specific example. Hopefully that made sense to you. But anyway, let's look at a specific example. And let's go back, let's do a different f of X equals X squared plus 2. So now that's never going to be negative because that's an upshift of a parabola sitting on the origin. And we're going to look on 0, 4. Okay, so we're going to show the intermediate value theorem holds, and find C when K equals 5. So we're gonna look at the height. Remember, K is a height. This is a height, right? This is a height of 5. So that's going to be strictly in between. So we got to show it holds. So let's graph this thing. So basically, it's an upshift of the X squared, right? And if I go from including 0 to including 4, my height at 0, if you plug in 0 to f of X, I get 2. And then if I plug in 4, what do I get? I actually get a height of 4 squared is 16 plus 2 is 18. So I'm not really drawing to scale there. It should be a little more vertical. But anyway, my height of 5 is strictly in between, right? So here's K equals 5. That's a height. Basically, I'm guaranteed that there is some C strictly in between 0 and 4 that actually maps to that height. Okay, so let me do this. So first of all, I'm going to redraw this picture because that was not really drawn to scale. So basically 0, 2, and then I go all the way up to 18 here. So there's 2, and 0 to 4 there. There's 4. So 4 is here. Basically, if I have a height of 5, so let me just redrawing it, I'd be here. and the C that maps to k equals 5 is there. So I got to find the C. I'm trying to find the C. So first of all, I got to show that F is continuous on the closed interval on 0 to 4, and it is. Why? Because it's poly, right? So I'm continuous on all real numbers. So F was x squared plus 2. That's a polynomial. So it's continuous on that closed interval because it's continuous everywhere. And then I have to show that f of a, which is f of 0, and f of b, which is f of 4, are not equal. So, right, this is my a, this is my b. So f of 0 is a height of 2, and f of 4 is a height of 18 by plugging those in, right? And basically, these are not equal. That's what we needed. So basically, we had a continuous function on a closed interval. We had the endpoints are not equal to each other. Then what are we guaranteed? Then there exists a C, which is strictly in between the endpoints, 0 to 4, strictly in between 0 and 4, such that what? F of C equals K, as long as K is strictly in between. So in this case, what do we have? We have that we need to show, so in this case, the left one is less. So f of 0 is less than K, which is 5, which is less than f of 4. Well, we have that because we have f of 0 is 2, is less than 5, is less than 18. So we have that as well. So there's 3 things we had to show. We had to show continuity, right? We had to show continuity on that closed interval. We had to show that the endpoints weren't equal, and we had to show that K was strictly in between the heights. K is a height between the endpoint heights. So the endpoints weren't equal, and if I have any height strictly in between, then there's going to be a function where f of c equals k. So let me do that in red. F of c equals k. So what is f of c? Well, f of x is x squared minus or plus 2 in this case. So this is going to be c squared. F of c, we plug c in everywhere there's an x. So it's c squared plus 2, and that equals k, which we said was 5 in this case. So in this case, to solve this, c squared equals 3, which says that c equals plus or minus the square root of 3. Square root of 3 is about 1.732. Remember, where does c have to be? C has to be strictly in between positive 0 and positive 4. So which one do I want? I want the positive one. So in this case, c is the positive square root of 3 is my answer there. And if I plug that into f, the square root of 3 quantity squared is 3 plus 2 gives me that height of 5. So in this case, my final answer is, since we wind the c, run out of room, but c equals the positive square root of 3. Once again, that's because I'm on the right side of that. If I drew the one on the left side, which I'll just, instead of redrawing everything, I'm just gonna use purple here. If I was looking at this side from negative 4 to 0, I'd still have the same height of 18 here. I'd still have the same height of 2, but this would drop down, and this c would equal the negative square root of 3, or negative 1.732, etc. So it is important that when you take the square root, you take plus or minus and then pick the one that's actually in the interval. But my interval was 0 to 4, and then not including the endpoints. So that's where the c was that I had to have, so I needed the positive square root of 3. All right, so those are the 2 theorems that I had not covered. Every once in a while, we get a really awkward number, right? And let's see. but let me continue with that one. We were working with f of x equals x squared plus 2, right? So if you can't solve it, we could get close, right? Now we can take square roots, we can solve any quadratic, but if this exponent wasn't a quadratic, if it was a kick or to the 4th power or to the 13th power, that's going to be very tough to solve. But what we could do is we could estimate it. So, and we can go out as far as you want. But if I plug in f of 1.5, 1.5 quantity squared is 2.25, right? Plus 2 would be 4.25. Now that's a little bit less than 5, isn't it? So it's bigger than that. So let's try 1.6. Well, if I square 1.6, I get 2.56, and then plus 2 is 4.56. I'm getting closer. Remember, what's my height I'm looking to hit? K equals 5. So 1.6 is closer than 1.5, right? 1.7, let's plug that in. Well, that's 2.89 when you square 1.7. 17 squared is 289, and then add 2, that's 4.89. So that's better yet. So C is closer to 1.7 than 1.6. So I don't want that one, I don't want that one, but let's try 1.8. If I square 1.8, 18 squared is 364. No, 324, sorry. So it's 3.24, and then plus 2, that's 5.24, right? Well, where's my K equals 5? It's right in between here. So K equals 5 is in between 4.89 and 5.24. So 1.7 to 1.8 is where my C is that I want. Well, we know because we actually solved it exactly, the square root of 3 is 1.732, et cetera, but I could go on now and I could try 1.73, 1.74, and then I know it's in between there. Then I could go to the nearest thousandth, et cetera. So if you have an awkward function, like if I've got f of x equals x to the 5th, plus 3x minus 2 or something like that, and you're trying to figure out what C is for a certain K equals whatever height you want. But basically what I may have to do is I may have to estimate. I know you guys have have in the past used a graphing calculator, and then if we have this function, and let's say it looks like this, I don't know what the scale is, but let's just say we were looking out here, here's your graph, and then my K is right here. Here's my height of K. Basically, if I'm trying to find that C value that maps to that, you could do a trace function. And when I do that trace function, you can just follow it along closer and closer until that point, and then you can get pretty close to estimating C on that. Well, we could do that. I basically did that trace function kind of from both sides. You could trace from the top too. But anyway, by plugging in points that are close and then getting closer and closer and get that. So if it says estimate, which I think it did on the last, I'm about out of time here. So on the last problem, it says, give me your answer within the nearest 2 decimal places. That's one way that you can do that. And then just real quick to finish up, because I don't want to keep you late on a Friday when you don't have other school. But if I was looking at something like g of x equals the greatest integer function of x and then minus a half, well, if we graph that thing, it's a downshift of that step function, right? So at minus a half and 1/2 there, basically, just so you know, the intermediate zero theorem does not apply on certain intervals. And why is that? Basically, just because endpoints might be different, one's positive, one's negative. Let's just go from a half x equals a half to x equals 3/2. Sorry. To x equals 3/2. From x equals 1/2 to x equals 3/2, basically the endpoints have different heights, right? One's positive, one's negative, but what's the problem? It's not continuous. My function is not continuous on the closed interval 1/2 to 3/2 because it has a jump or essential discontinuity in between, right? So because I have that discontinuity and that jump right here, so we can't use the intermediate zero theorem, so or the intermediate value theorem there either, because we don't have continuity on the closed interval. So having continuity and being able to draw that graph without lifting your pen, very important. So I'm going to stick around for questions, just in case some of you have time available. So wish you the best tonight and on your weekend activities. Stay safe and healthy, and I will see you. The plan is in class on Monday, but your 1.9 is due. The evens are due on Monday. I will do 1.10 and then, of course, continue working on con over everything I've covered that's in there. And then we will be finishing up and having our full chapter test next week. All right, and I'll stick around for questions, but I'll stop recording.